Let's talk about improper integrals type 2, where we have infinite discontinuities. So if we have a continuous function, but it has a discontinuity at one of the bounds of integration, at one of the values a or b. If we have an infinite discontinuity, what we can do is we can replace that bound in the integral. So in this first case, suppose that it's discontinuous at x equals b. We can replace b with t and take the limit as t is approaching b from the left. And if that limit exists, then the integral will be equal to that limit, and we will call it convergent, as you can see down below. Convergence is if the limit exists. If the limit does not exist, then we say that the integral is divergent, and that does include infinite behavior if the limit is infinite. And of course, if the discontinuity is at the left-hand bound, at the lower bound, then we replace that lower bound with t, and then we let t approach a from the right, and we consider what that limit is. So let's take a look. So if we had just some visuals here, if we had an infinite discontinuity at b for our first function, but we wanted the integral from a to b. Well, when we notice that infinite discontinuity, we say, well, what we're going to do is we're going to replace that in the integral with t, and we're going to take the limit as t is approaching b from the right and consider what happens here. We will integrate as we did with the type 1 improper integrals. We will integrate first, and then we will evaluate across the bounds and take the limit second. So if the infinite discontinuity, on the other hand, let's suppose that we had an infinite discontinuity at x equals a, but we wanted to integrate our function from a to b, then what we'll do is we'll replace that lower bound with t, take the limit as t is approaching a from the left, and integrate. And we'll do our process of integration, and then we will simply take the limit and see if that limit exists. If the limit exists, we say the integral is convergent. If it does not, we say it is divergent. Now, what we can also do is suppose that we had a integral from a to c, but we had from a to b, but in between a and b, we had a discontinuity. Somewhere in between a and b, we had a discontinuity, and we wanted to integrate all the way from a to b. Well, what we can do is we can just split it up at that discontinuity, split it into two integrals, and then examine each one of those. And if they both are convergent, then the integral itself from a to b will be convergent, and we'll add up the two. So we'll think about that when we get to one of those. So that would look something like if we happen to have, let's say, an infinite discontinuity right here, and we wanted to integrate from a to b, but right here we had that infinite discontinuity. What we could do is we could integrate from a to c, see if that integral existed, and then integrate from c to b, see if that integral exists. Look at that as an improper integral. See if that integral is convergent, if it has a value, and if it does, then we could add the two together. Okay, so let's take a look at a few examples. All right, let's start with this one. So suppose that we want to evaluate or state that the following integrals diverge. So on this particular one, we're integrating from 0 to pi over 2 the tangent of x. And it might help to think about a quick little recall, because the problem here, the reason this is improper, is because of this upper bound of integration at pi over 2. And that happens to be a vertical asymptote for the tangent curve. So if we think about the tangent curve looks something like this, and it is periodic, so it continues. But right here at pi over 2, we definitely have a vertical asymptote. So that is some interesting behavior. Essentially, if we wanted to think in terms of areas, what we're asking right here is what is the area, because this is a positive curve, what is the area under the tangent curve to the x-axis from 0 to pi over 2? But that area does extend up along that vertical asymptote. So the question would be, is that area that is being trapped there between the function and the x-axis, is that finite or infinite? And we won't know until we compute this improper integral. So we're going to go ahead and replace that upper bound with t. We're taking the integral of the tangent of x, and we're going to let t approach pi over 2 from the left. So we're evaluating this as we approach pi over 2 from the left. So now what we're going to do is we're going to do the integral first. So remember, when we evaluate improper integrals, we do the integral. So we're going to work on the integral, and then second, we will evaluate the limit of the result of the integral after we've plugged in our bounds. So that's the process that we're going to go through, and I erased part of my directions. So I will write them back in. And if we remember, the integral of the tangent was actually one of our useful integrals. So this is going to be the limit as t approaches pi over 2 from the left. This becomes the natural log of the absolute value of the secant of x, and we're evaluating it from 0 to t. So we continue with the evaluation of the integral across those bounds, and we get the natural log of the absolute value of the secant of t minus the natural log of the absolute value of the secant of 0. Well, the secant of 0 is 1, so this becomes the natural log of 1, and the natural log of 1 is 0. So this piece becomes 0, and what we need to do is we need to think about what is happening to the natural log of the secant of t. Now, you could either think about, I did a little graph here of the tangent curve. We could also graph, if we wanted to, we could also graph the secant and have a graphical reasoning here for what that limit of the secant is as t is approaching pi over 2. So we could graph, if we wanted to, we could graph the secant graph, and I do that by thinking about what does the cosine graph look like, and it looks something like this, and therefore at the zeros of the cosine graph we have vertical asymptotes for the secant, and here's pi over 2, and so the secant graph is going to have behavior that looks like that. So as we approach, again with limits, as we're approaching that pi over 2 and we're coming from the left, the secant is approaching positive infinity. Another way to think of that, you could also think of this as the natural log of 1 over the cosine of x, and 1 over the cosine of x. Well, the cosine is approaching 0, but it is approaching 0 in a positive manner, so you could also think of it that way. But this is the natural log of a quantity that is approaching positive infinity. We are also subtracting 0 if we want to bring down that last term. So as we approach infinity, the natural log of something that's approaching infinity is itself infinite. And so this ends up having a limit that is infinite, and therefore it is diverging. So this diverges. So this integral diverges that area, if we're thinking in terms of area that I have highlighted there in red. That area right there is actually infinite. As the tangent approaches that asymptote, it is gathering an infinite amount of area between the curve and the x-axis and that asymptote. And so we're getting that infinite amount of area. We say that that integral is diverging, or it diverges. All right, let's look at another one. Okay, so let's take a look at this guy. So we're taking the integral of the natural log of x over the square root of x dx from 0 to 1. Now, I'm not going to give the graph of this if we really wanted to. This is not a graph that I think that we would just know off the top of our heads, but we could go to a graphing utility like Desmos to graph it. But I think that we can see right away that this is going to have a vertical asymptote. When I plug in 0 right here, we're going to get division by 0. And that is definitely going to create a vertical asymptote. We also have the natural log of x, and as we're approaching 0, that itself has a vertical asymptote. So we've got some stuff happening here, and 0 is the problem area. So we're going to take the limit of the integral from t to 1. We're going to let t be approaching 0. This time we're going to be coming from the right side of 0 because our interval is from 0 to 1. So we're going to be coming from the right side of 0 of the integral of the natural log of x over the square root of x dx. Now, this particular one, it might help if we wrote it this way. This is the limit as t is approaching 0 from the right, because we have to figure out how we want to integrate that. So from t to 1 of the natural log of x times x to the minus 1/2 dx. And, I don't know if we want to write it that way or if we want to leave it as it was initially. But either way, I'm looking at that and I'm thinking, how do I want to integrate that? And I'm seeing a product. And so since I have to do the integral first, and then I come back and I do the limit after the integral, so we integrate first, and then we take the limit second. And again, what's sort of fun about these improper integrals are we're practicing two major skills. One out of Calculus 2, integration techniques, and the other skill, taking limits, coming out of Calculus 1. So we're practicing two major calculus skills in this section, kind of pulling those two things together with improper integrals. But I do have to integrate first. I'm seeing that product, whether we see it here or we see right here, we think of that. We could also think of that as the natural log of x times 1 over the square root of x. But either way, it's definitely integration by parts seems to be a good route to go. So we'll go integration by parts. Because we have a natural log in there, that tends to be a good choice for u. So I'm going to let u equal the natural log of x. I'm going to let my dv be the rest of the integral. So x to the minus 1/2 dx. And du then, of course, is 1 over x dx. And v, when I integrate that, becomes x to the positive 1/2 divided by 1/2. So 2x to the 1/2. And we're going to go ahead and finish out that integration by parts. Let's get it back in here. Again, carry the limit. We will carry that limit along. And we've got our u times v, so we have 2 times x to the 1/2 times the natural log of x minus the integral of, we end up with 2x to the 1/2 over x dx. I'm going to simplify that a little bit before I take and evaluate. We're going to plug in those bounds. Again, we're going from t to 1. We'll plug in those bounds, but I'm going to get this fully integrated first. So limit as t is approaching 0 from the right, we've got 2x to the 1/2 natural log of x. This is going to become minus the integral of 2x to the minus 1/2 dx. When we get done, we'll evaluate from t to 1. Keep going, limit as t is approaching 0, just carrying the limit and the bounds down until I get this fully integrated. This is going to become minus 4x to the 1/2, because when I integrate, I get x to the 1/2 and I divide by 1/2, which is the same as multiplying by 2. So then I've got that 4x to the 1/2. Now I'm evaluating that from t to 1, and let's see what that ends up being. So then we've got the limit as t is approaching 0 from the right. When I plug in 1, I'm going to go ahead and get 2 times the natural log of 1, so that's going to be 0, minus 4 times 1. So 4 times 1, square root of 1 is 1. Minus, and then I'm going to get 2t to the 1/2 natural log of t minus 4t to the 1/2. Okay, and we just keep rocking and rolling here and finishing this out. And so this is going to be the limit as t is approaching 0 from the right. Let's get this simplified before we take the limit. In this first term right here, the natural log of 1 is 0, so I just get a minus 4 minus 2t to the 1/2 natural log of t minus a minus, so plus 4t to the 1/2. Whew, okay. So we've got our integral through integration by parts. Now I can focus in on taking the limit. So how do I take the limit of this? So first of all, when I take the limit of a constant, it will be a constant. So we will have a minus 4. What is happening? I'm scribbling out instead of highlighting. So we'll have a minus 4. We'll have the minus 4, and then when we take this limit, something kind of interesting happens, but when I take this limit, this will go to 0. Okay, so what happens right here? Well, when I take this limit, I get a 0 times a negative infinity, and that is indeterminate. So it's indeterminate, but it's not of the form I can apply L'Hopital's rule in. I'd have to have 0 over 0 or infinity over infinity, so I need to drop one of those functions. So I'm going to go ahead and drop that t to the 1/2. But I wanted to highlight that minus 4. I still have that minus 4, so I'm going to bring that outside the limit. So I have minus 4, and then I'm adding the limit as t goes to 0. Now I got some work to do here. So I've got a minus 2 natural log of t over, and I'm going to drop that t to the minus 1/2 right there. Okay, so doing a little bit of work because I saw that indeterminate form. When I take just this limit now, I end up getting an infinity, because it's negative 2 times a negative infinity when I approach 0, over, now when I drop this down, I dropped a negative. When I drop that t to the 1/2 to the denominator, I had to change the power. And I had a little frog in my throat, and I missed that as I was writing it. So this is t to the minus 1/2. So when I'm approaching 0, this is 1 over 0 or infinity. So this is approaching now, as we approach 0, this ratio of these two functions is approaching infinity over infinity, which leads me the ability to now apply L'Hopital's rule. Now, don't forget, I still have this constant. It's just kind of floating out there in front for now. But I have that constant minus 4. So we've still got that constant minus 4. We're still taking the limit, but now we're applying L'Hopital's rule. So I'm going to take the derivative of the top. So I get minus 2 over t, minus 2 times 1 over t. And when I take the derivative in the bottom, I'm going to get minus 1/2 t to the minus 3/2. Now, that right there is messy, and I don't want to take the limit until I get it simplified. So here in red, I'm just going to simplify that. So that's minus 2 over t, and we're dividing by minus 1 over 2t to the 3/2. So that becomes minus 2 over t times a negative 2t to the 3/2 all over 1. And that ends up becoming a positive 4t to the 1/2, just doing the algebra. So when I'm doing this, I get the negative 4 still floating out in front. Now I'm taking the limit as t is approaching 0. And I'm taking the limit of 4t to the 1/2. Now notice all of this work has really been focusing in on that one piece. Somehow I'm managing to scribble on my notes. It was all focused in on that one piece right there. We're taking that limit, we end up with that indeterminate form, infinity over infinity, and now I'm applying it, taking the derivative, simplifying, but now I can finally take the limit. So let me get rid of some of my highlights here so it's not too much, but just wanted to follow through where we were at there. So now we're taking the limit as t is approaching 0. We still have that minus 4, but when I take the limit now I end up with 4 times the square root of 0, which of course is just 0. And so my result ends up being minus 4, which of course is a finite value, and so that means that this integral is converging. So this means that this integral from the beginning, if we can get it up there, this integral was converging, and it is converging to negative 4. Okay, let's do one more. This particular one has a vertical asymptote as well. And it is at, when I look at this function, I see that I have a vertical asymptote at x equals 2. But I'm looking at the interval from 1 to 4. Well, guess what happens? 2 falls right smack, well, not right in the middle, but it falls in between 1 and 4. So when I see this, I think, oh, you know what I'm going to have to do here? I have to break this up. I have to integrate from 1 to 2 of 1 over x minus 2 to the 2/3 dx. I have to see if that integral converges. If it does converge, then I'm going to look at the integral from 2 to 4 of 1 over x minus 2 to the 2/3 dx. And I'll see if that integral converges. If they both converge, then I will be able to add the 2, and the integral from 1 to 4 will be converging to whatever that value is when I add the 2. But I have to notice that 2 is falling between 1 and 4, and that is where I have that vertical asymptote. So I've got to break this apart into 2 integrals. And then I have to consider each one. So let's go ahead. So let's do the first integral. So if we're integrating from 1 to 2 of 1 over x minus 2 to the 2/3 dx, replace the 2 where we've got the issue. We're going to replace that with a t. So we're going from 1 to t. Sometimes it can help. I'm super visual, so it can help me. We're thinking of this from 1 to 4. And here's 2, and we're splitting this up into 2 intervals, 1 and 2. On the first one, we're going to be approaching 2 from the left side. So on this one, we're replacing the 2 with t. We're taking the limit as t is approaching 2 from the left. And we've got 1 over x minus 2 to the 2/3 dx. Now we're going to go ahead and integrate that. And on this one, we're going to want to do a u substitution. So if u equals x minus 2, then du is dx. So we can make that simple little substitution right there. So this is integral as t is approaching 2 from the left. We're going to have the integral from 1 to t. This is going to become 1 over u to the 2/3. But I'm going to go ahead and write that as u to the minus 2/3. U to the minus 2/3 and du becomes dx. So now we can integrate that. We still haven't taken the limit, so this is still the limit as t is approaching 2 from the left. We're going to end up with u to the 1/3 divided by 1/3, which is 3. So 3 times u to the 1/3 evaluated from 1 to t. But we got to make sure we plug our u back in because these were x's, x equals 1 and x equals t. So this is the limit as t is approaching 2 from the left. We've got 3 times x minus 2 to the 1/3 minus 3 times, and we're going to go ahead and plug in, oh wait, we still haven't plugged in our bounds. Oops, I was jumping ahead of myself there. We're going to go ahead and plug in the x minus 2, and then we're going to evaluate this from x equals 1 to x equals t. Now we're going to plug in our t's so that we can take the limit as t is approaching 2 from the left. So this is 3 times t minus 2 to the 1/3 minus 3 times 1 minus 2 to the 1/3. Well, 1 minus 2 to the 1/3, so that's a negative 3 times a negative 1. Cube root of negative 1 is negative 1. So this ends up becoming 3. And we've got 3 times t minus 2 to the 1/3. And we still need to take the limit as t approaches 2 from the left. Okay, now we're ready. We can go ahead and plug in 2 from the left, and this ends up becoming just 3 times 0 plus 3, and this is 3. This is a finite value. The limit does have a value, so that means this integral is converging, and it is converging to 3. So our first integral, that was this piece, 1. So this integral is approaching 3. I'm going to move my little picture right here. I'm going to move that up top right here because we have just figured out that my first integral has a value of 3. So now the question is, what's happening with my second integral? Does that have a value from 2 to 4? So let's take a look at the second. Let's squeeze it in over here. No, we'll do it down below. So 2. So what's happening at 2? So that's the integral from 2 to 4 of 1 over x minus 2 to the 2/3 dx. And so we're taking the limit of the integral from t to 4 as t is approaching. And again, if we think about, we're coming up here, if I look at this little picture at the very top, this time we're working on this side. This time we're approaching 2 from the right. So as t is approaching 2 from the right, integral from t to 4 of 1 over x minus 2 to the 2/3 dx. Now I'm going to go ahead and zoom in because it's getting really small down at the bottom of the screen. So let's go ahead and zoom in. This is going to be very similar work for the integral, although the bounds are different, but the u is still going to be x minus 2. We do a little u substitution, du equals dx, and this ends up becoming the limit as t is approaching 2 from the right, integral from t to 4 of 1 over u to the 2/3, but I'm going to write that as u to the minus 2/3 du. Replace the dx with the du, and this ends up becoming the limit as t is approaching 2 from the right of 3u to the 1/3, and that is the limit as t is approaching 2 from the right of 3 times x minus 2 to the 1/3, or the cube root of that quantity, evaluated from t to 4, and that ends up being the limit as t is approaching 2 from the right of, now let's plug in our bounds. So we get 3 times 2 to the 1/3 minus 3 times t minus 2 to the 1/3. And we're evaluating this as t is approaching 2. So as t approaches 2, of course, this first quantity is just a constant. That's 3 times the cube root of 2, or we could leave it as 3 times 2 to the 1/3. Minus, well, when we plug in 2 here, 2 from the right, that becomes 0 to the 1/3, so that's 3 times 0. And so this value is 3 times the cube root of 2, which of course is a finite value, and so this second interval is also converging. And therefore, our integral converges because each piece converges, and the integral is 3 plus 3 times the cube root of 2. And that is our answer. So our answer is, we could write that as 3 times 1 plus the cube root of 2, or we could leave it the way it was initially as 2 separate terms, 3 plus 3 times the cube root of 2. But either way, we definitely are getting a converging integral, but on that particular one, we had to look at both pieces. And I know it's really small to try to get it all on one screen there, but we did have to look at two pieces because that vertical asymptote fell right in the middle, not right in the middle, but it fell in between the two bounds that we were integrating across.